Okay, so let's revisit really quickly the superposition principle, and then I want to show you a more interesting application of this principle than in the previous video. So really quickly, just bear with me. So we have the following non-homogeneous differential equation, and so, or wait, let me restate that. We have two second-order non-homogeneous differential equations. Now, what we're told is y sub 1 is the solution to the first equation. Y sub 2 is the solution to the second equation. The principle says then for any constants, now we use C, but k sub 1, k sub 2, the function, now notice what they're doing is they're taking, they're attaching a constant to the first solution. They're attaching a constant to the second solution. But the function k sub 1, y sub 1 plus k sub 2, y sub 2 is the solution to the differential equation of this form, right? So notice that the form that we have here matches the form that we have of our solutions, and that's the idea. Now, what I want to do is, and we're gonna jump into this and teach this via an example. What I want to be able to do is look. Let's say I have a particular solution to this non-homogeneous equation. Okay. In other words, y equals, and I would write something here. I already have the solution. What I want to know is how do I, from that, find a general solution to a non-homogeneous equation? Because once I have the general solution to a non-homogeneous equation, if the variables change on me, in other words, if the conditions change on me, I can just adjust the conditions so I can find a new particular solution. Right? I need to be able to get to a general solution so that I can, for any conditions that come about, I can always find the next particular solution. Does that make sense? We have to have a way of getting to a general solution to these non-homogeneous equations. And this superposition principle is actually really, really helpful. So let me start, and I know that this is a whole block of text, so please wait just a second. Wait, let me go through the explanation, then pause it, then write. Okay, just hold on for just a second. So notice that I'm given, or at least I'm told, that the following is a particular solution to this differential equation. Okay, so let's make sense of this. So this is a particular solution to this differential equation. Now, what do they want? Well, the first thing they want is for me to find the general solution to this differential equation, right? So how do I go from particular solution to a non-homogeneous equation to a general solution to a non-homogeneous equation? And bear with me here. Well, look, I'll already tell you right now, this t squared was given, right? That's going to end up going here. It's to do it. Let me read. The general solution to a non-homogeneous equation, now that's what I want, is equal to the particular solution to the non-homogeneous equation. Now I already have that, plus the general solution to the homogeneous equation. So do you see how we're just taking the sum of a general solution to an homogeneous equation plus a particular solution to a non-homogeneous equation? That gets me to this new general solution to non-homogeneous equations. If this language is tripping you up, you need to pause this and make sure you understand what I mean by homogeneous, non-homogeneous, general, particular. The language is not that thick that you can't just pause it right now. Remember, f of t is non-homogeneous. So if it's set equal to 0, that's homogeneous. General solutions mean it's one of an infinite, a whole family of solutions. Particular solutions are one particular solution under certain particular conditions. All right, so first things first, we're going to find the general solution. And then, look, these conditions, they changed on me. So I want to be able to find the new particular solution. And I can do that if I can first get the general solution. All right, now feel free to pause the video, write down everything I have here if you'd like. And then when you're ready, let's go ahead and unpause it and let's start with this example. Okay. So what I'm given, what I'm told is I have a particular solution to this second order differential equation. And what I'm trying to do, right? Remember, our job is to find the general solution. All right, now the way we're going to do this is we're going to first go back to homogeneous equations. We're going to pretend like for a second, we're going to just assume that we had y double prime minus y is equal to 0. Now that would be a homogeneous equation. Now I know that I don't really have it equal to 0. I get that. But what we're going to do is we're going to go back to the beginning of chapter 4 and where we were dealing with just homogeneous equations. And I'm going to go ahead right now and get from here to auxiliary form. Right, so you with me that A is equal to 1, B is equal to 0, and C is equal to negative 1. So let's get to the auxiliary form. So this would be 1r squared minus, so this, the R or the BR would zero out, and this would just be minus 1 equals 0. Now, I don't need a quadratic equation or anything for this. This is just r squared is equal to 1, or r is equal to plus, r is equal to plus or minus 1. Okay, now that's what I need. Why did I write r is equal to plus or minus r? How about this? R is equal to plus or minus 1. All right, so here we go. So r sub 1, one of the roots would be positive 1. The other root would be negative 1. Okay. Now, the general solutions for homogeneous, same rules apply, whether you have, when it comes to the roots, right? Whether you have double roots, single roots, or no matching roots. In this particular case, let's go ahead and write the general solution to these homogeneous equations. We have C sub 1 e to the r sub 1 t plus C sub 2 e to the r sub 2 t. Remember this? Now, I know r sub 1 and I know r sub 2. So I can plug these in, which I'm going to do right now. And then what would I have? I would have the general solution to a homogeneous equation. So let's go ahead and write that. So here it is. C sub 1 e to the, I'm going to plug in 1, so that would just be t, plus C sub 2 e, I'm going to plug in negative 1, so that's negative t. All right. Now follow me up here. So this is the general solution that I want, the one to the non-homogeneous equation. And I can get that by as long as I have a particular solution, which I do, plus the general solution to the homogeneous form. So simple enough, this y of t, the general solution, let's start with, it's going to be the particular solution, which was t squared, plus the general solution to the non-homogeneous form. All right, now that is, and I'm going to write it, that is the general solution to the non-homogeneous, right? Because this is not equal to 0 to non-homogeneous. Give myself enough space here. Okay. Now, at this point, as long as I have some conditions, some initial values, I can start to generate new particular solutions, right? So if the particle is moving, I have obviously now I have new initial conditions. So I can start to produce new particular conditions, so I can start to produce new particular equations, solutions. So I'm now going to go to the next page, and I'm going to grab these new conditions, right? It says, so let's find the solutions that satisfy some new conditions. Y of 0 equals 1, y prime of 0 equals 0. All right, so here is this set of new conditions. And I can get to a new particular solution from this general solution. All right, so what does that involve? Well, first off, clearly I'm going to need y prime, because I got to set y prime equal to 0 so that I can plug 0 in for t. So let me go ahead right now and find y prime. All right, well, so we're going to take the derivative with respect to t. So this is going to be 2t plus, well, this is pretty darn simple, right? This is going to be derivative of e to the t is just e to the t. And then this last one, since I have the derivative of e to the negative t, this is going to be minus c sub 2 e to the negative t. Okay, well, this is stuff, a road we've been down before, right? So let's start with the first condition that has to do with just y. So we're gonna plug 0 in for t, and we're gonna set this equal to 1. Let's do that right now. So that would be 1 is equal to, well, this is going to be, well, actually, I tell you what, let's do it like this. I got 0 is equal to, let's plug in, oh man, I'm so sorry, I'm looking at the derivative. Try that one more time. So I'm going to be plugging in 1, 0 for t, and 1 is what I'm going to be setting it equal to. Okay. So 1 is equal to, well, 0 squared is 0. C sub 1, e to the 0 is just c sub 1. And then I got c sub 2, e to the 0 is just c sub 2. All right, so my apologies, I was getting ahead of myself. Too excited. All right, now let's look at the condition for the first derivative. So obviously I'm going to be setting that derivative equal to 0 and plugging the zeros in for the t's. So in this case, I get 0 is equal to, well, c sub 1 e to the 0 is just c sub 1. Don't forget about that minus. C sub 2 e to the 0 is just c sub 2. All right. Now this is a very simple system. And I don't care how you do it. If you want to use a matrix, if you want to just use some elimination methods, what you should find is c sub 1 is equal to 1/2, and c sub 2 is also equal to 1/2. All right, we'll just make sure that that makes sense. And so if you have a half plus a half, you get 1. If you have a half minus a half, you get 0. Okay, so do not stop here. Your goal is to take this information and plug it into the general solution so that you have a particular solution. All right, so the particular solution is going to be t squared plus half e to the t plus half e to the negative t. That is the new particular solution. Okay, so we're going to go ahead and conclude 4.5. And the next, where we're going next, the very last chapter of section of chapter 4, is we're just going to try to formalize these methods a little bit, right? Because we need a little bit more formal of an approach, right? We need a playbook, in other words. So I'm going to go ahead and call it quits, and I'll see you in the next video.